let's discuss the effects of temperature and doping on the mobility. Here, the mobility of the electrons and the holes is actually influenced by the lattice scattering and the impurity scattering. These two are the process on which this mobility actually depends. So it mainly depends upon lattice scattering and impurity scattering. Then what's this lattice and the impurity scattering? First, let's discuss about this lattice scattering. Lattice scattering means if I consider one semiconductor, then when I increase the temperature, here is my temperature, okay? When I increase the temperature of it, then the vibration in the charge carriers, that also increases. If here is one electron, then here also some electrons. Then if I increase this temperature, then there is a more random motion of these electrons. This electron, the mean free path becomes less. That means it takes very less time for the collision. So when we increase the temperature in this semiconductor, the vibration also increases. Vibration increases means this mobility decreases. So we can write this as, at the higher temperature, this T is inversely proportional to the mobility. As the T increases, this mobility decreases. So this temperature, it depends upon the doping of the mobility. And now let's see the impurity scattering. It is at the higher temperature, it's mainly at the higher temperature. But if we consider this impurity scattering, this comes in the lower temperature. At lower temperature, this impurity scattering is dominant when compared to this lattice scattering. So impurity scattering means it is the scattering due to the crystal defects or any impurity atoms, collision with the impurity atoms. That one is the impurity scattering. Consider this is in some less temperature. Then if I supply some temperature, the electrons which is nearer to this get more temperature, but the electrons at the cooler lattice or less agitated, there the thermal motion is slow. That means slow movement of electrons when compared to these electrons. Here the more thermal motion is there, but here the less, due to it's somewhat cold when compared here. So it's a slow movement. Slow movement means its interaction with the charged ion is more. That means a strong interaction between these slow moving electrons and the charged ions. So in this case, it is the lattice scattering, okay? Then in the second case, we can write this temperature is directly proportional to mobility. That means when the temperature decreases, this mobility also decreases. As it increases, this mobility also increases. But in this case, this temperature is directly proportional to 1 by mu. It is at the higher temperatures. So, if we draw the graph, now let's draw the graph. Okay. Now, if we draw the graph versus the temperature and the mobility, this is my temperature and this is my mobility. It comes like for impurity scattering. I told in the impurity scattering, it is like the mobility is directly proportional to the temperature. That means as this temperature increases, this also increases. And then this for the impurity scattering. And in the lattice scattering, as the temperature increases, this mobility decreases. That's inversely proportional. So it comes like this. This is the graph. Approximate temperature dependencies for this impurity scattering is T to the power of minus 1 by 2, and for this for lattice scattering, it's T to the power of 1 by 2. This for impurity scattering and lattice scattering. Impurity and this for lattice. Okay, this is the graph. If we draw the graph of temperature versus resistivity and the conductivity. Now let's draw the graph of temperature versus the resistivity, that's rho. Then in the semiconductor, it is like this. Okay, it's for experimental observation. It's like this. And conductivity means exactly opposite of this. So I can draw this as, it is for the semiconductor. Okay, it is like this. T and here the sigma, conductivity. And in case of metals, it is like in this way. It's not a constant one because it depends upon the type of metals or type of semiconductor we chosen. It's just a general case. And here if we draw the temperature versus conductivity for the metals, exactly opposite means it's like this. Okay, this is the graph. You need to remember this one. What is this light scattering and the impurity scattering effects of temperature on this mobility? Thank you.